All right, everybody, what is going on? Got another statistics video for you. This one's on measures of variation. We're going to talk about standard deviation and variance and range, and we're going to look at Chebyshev's theorem. All right, so let's go ahead and get started. All right, so first off, let's just look at the range. The range is the difference between the largest and smallest values of a data distribution. All right, so let's just look at this example real quick, and then what this is going to do, this is going to lead us into standard deviation and variance. So we have a large bakery orders cartons of Maine blueberries. The average weight of the cartons is supposed to be 22 ounces. Random supplies of cartons from 2 suppliers were weighed. The weights in ounces of the cartons were this, and so supplier 1, these were the weights of the 5 different cartons they sampled, and these were the weights from supplier 2, and they want us to compute the range of carton weights from each supplier. So for supplier 1, we'll just label it S1. The largest value is 27 minus the smallest value, which is 17, and that equals 10. And then for supplier 2, the largest value is 27 minus the smallest value, 17, and that is 10. And then they want us to compute the mean weight of cartons. So supplier 1, you should know how to find the mean. That was done in the last video, or the video before last. It was an earlier video on mean. So basically we just add all the values up. So 17 plus 22 plus 22 plus 22 plus 27. That gives us 17 plus 22 plus 22 plus 22 plus 27, and then we divide that by 5 and we get 22. So we get x bar is equal to, let's see, is 110 over 5, which equals 22. And then for supplier 2, we add those up. 17 plus 19 plus 20 plus 27 plus 27. That is equal to 110 divided by 5. That is also 22. All right. So what does that tell us anything? Does that give us anything different? Well, if we look at this, we can see that the range is the same on both of them and the mean is the same on both of them. But if you look at supplier 1 versus supplier 2, notice more of the values from supplier 1 are closer to the mean than those values from supplier 2. You see that? So the range tells us the difference between the largest and smallest values, but it doesn't tell us how much the other values, how much they vary from one another, or how much they vary from the mean. So we need something that can tell us this, and that's where variance and standard deviation come from. Well, that come in. Not come from, but that's where it comes in. So let's look at that. Let's look at variance and standard deviation. So we've got the sample variance and the sample standard deviation. This is sample standard deviation. For some reason I didn't put sample there. All right, so S squared, that's the variance. And you notice we have 2 formulas here, okay? Now, this formula, the sum of x minus x bar, all that in parentheses, squared divided by n minus 1. And then we have this formula, the sum of x squared minus the sum of x, all of that squared divided by n over n minus 1. Okay, so what's obviously the formulas are different, but they're going to give you the same result. Okay, the results will be the same. This one is the computation formula. This one, I mean, you can use either one. It doesn't matter. You'll get the same answer either way. It's just that this one tends to be easier to calculate. Okay? And, as far as which one you want to use, that's up to you. Okay? Or whatever your teacher tells you. I mean, I'm going to use the computation formula. I just think it's easier to set up and use and everything. This one, you would just have to take each data value and subtract the mean from it and then square those results. Okay, but I'll use this one. And the standard deviation, notice the standard deviation, the formula is exactly the same as the variance. It's just we're taking the square root. And once again, this is the computation formula. Now, I will say this. If you're taking a statistics class or doing something in statistics in one of your classes, and you look at this formula that I have for standard deviation and you say, well, that's not what the formula looks like that my teacher showed me. And that may be correct. It may not look like that. So I remember a long time ago, I made a video on just standard deviation. That was it. It was just one example of how to calculate standard deviation. It wasn't a lecture video. And I was going into some textbooks I had, looking for some examples to work. And I noticed one thing. I had 3 different books, 2 statistics book and 1 finite math book that had a statistics section in it. And I looked at the formulas they had for standard deviation. And do you know, in each one of those books, the formula was different? I mean, it was the same, but it was written different. So if your formula is different than the one I'm showing you, that very well could be the case. Okay, but you're going to get the same result. And that's why I emphasize the important thing is don't memorize how I'm working these things, but understand what the symbols mean. Okay, understand what this sum of x squared means. Understand what this sum of x means. Remember, this symbol here means sum. We did that in the earlier video when we talked about mean. And n is the number of data values. Okay. All right. So with that being said, let's look at this example here. It says Big Blossom Greenhouse was commissioned to develop an extra large rose for the Rose Bowl parade. A random sample of blossoms from hybrid A bushes yielded the following diameters in inches for mature peak blossoms: 2, 3, 3, 8, 10, and 10. Find the sample variance and sample standard deviation. All right, so here we go. All right, we're going to use this formula here. We'll use it without the square root, to find the variance. But let's just look. We have to find the same thing in both of them. Once we calculate the variance, we just take the square root of that, and that gives us the standard deviation. So what do we need? We need the sum of the x values, and we need the sum of the x squared values. Okay? I want you to understand that this and this are 2 different things. This one right here means to sum those values. Just add them up. This right here means to square each one of those and then add them up. Okay? All right. So what I like to do, I like to make a column x, and x squared. Make two columns. We got 2, 3, 3, 8, 10, 10. And now those are our x values. Now let's square each one. So that's 4, 9, 9, 64, 100, 100. Now, what do I need to do? Well, look, I need to sum the x values. So I need to sum this first column, and I need to sum the x squared values. I need to sum this column. So let's do that real quick. So the sum of the x values, all right, that is going to be 2 plus 3 plus 3 plus 8 plus 10 plus 10. That is 36. And the sum of the x squared values, that's 4 plus 9 plus 9 plus 64 plus 200. That is 286. All right. So now let's write our formula down. So we've got s squared is equal to the sum of x squared minus the sum of x, all of that squared, over n, and then all that divided by n minus 1. That's our variance. Okay? So look, this is all we do. We get s squared is equal to the sum of x squared. What's the sum of x squared? It's 286. Minus the sum of x. Well, what's the sum of x? That's 36, and that is squared, and that's divided by n. So what is n? N is, what do we have? 1, 2, 3, 4, 5, 6 values. And then that's divided by n minus 1. And so there you have it. Let me make this look a little better. Let's put the s squared equals right there. And then when you plug all of this into your calculator, you get 286 minus 36 squared divided by 6, and then divide that by 5. We get 14. All right. So this is your sample variance. And then the sample standard deviation is just the square root of the variance, which is the square root of 14, which the square root of 14 is 3.74. And so there's your variance, your sample variance and sample standard deviation. And that's all there is to it. I mean, you just gotta, basically all you're doing is you look, well, here's a formula. You just look at the formula and see what you need. You make columns for those. You need the sum of x. You need the sum of x squared. And that's it. All right, so let's look at this one. It says, Big Blossom Greenhouse gathered another random sample of mature peak blooms from hybrid B. The 6 blossoms had the following widths in inches. So right here. And they want us to find the sample variance and the standard deviation. All right, so once again, let's do the same thing. Yes, there's a reason that I'm working the same type of problem twice in a row. So we got 5, 5, 5, 6, 7, and 8. And then we square each one. That's 25, 25, 25, 36, 49, and 64. And we will need the sum of each one, the sum of the x values. That is, let's see, that's 15 plus 6 plus 7 plus 8. That is 36. And the sum of x squared, 25 plus 25 plus 25 plus 36 plus 49 plus 64. That is 224. All right. All right. So let's look at this. So remember, we've got the variance is equal to, that's going to be the sum of x squared minus the sum of x squared over n divided by n minus 1. So we get s squared is equal to the sum of x squared, which is 224, minus the sum of x, and then all of that squared, that's 36 squared over n, which is n is 1, 2, 3, 4, 5, 6 over 6 minus 1. And so that is going to give us 224 minus 36 squared divided by 6, and then divide that by 5, and we get 1.6 for the variance. And so the standard deviation is the square root of s squared, which is the square root of 1.6, which the square root of 1.6 is 1.26. Okay, so that's great and everything. We know how to find the variance and standard deviation, but it's really kind of useless of finding all this stuff if we don't know what we're actually doing, if we don't know what we're finding. So let's come back up here and let's find the mean x bar. That's 2 plus 3 plus 3 plus 8 plus 10 plus 10 divided by 6, and I believe that is, let's see, 10, 20, that's 20, 36. That's 36 over 6, which equals 6. So remember, this is hybrid A. Okay, hybrid A has a mean of 6. And let's look at hybrid B. X bar equals 5 plus 5 plus 5 plus 6 plus 7 plus 8 over 6. See, that this right here is 15 plus 15 is 30 plus 6 is 36 over 6, which equals 6. Oh, look at that. You see that? The mean for each one of them is the same. So let's just look at that. So we've got hybrid, we've got hybrid A has a mean of 6, and standard deviation, what was it? 3.74. 3.74 inches. And hybrid, well, keep wanting to spell hybrid wrong. Hybrid B has a mean of 6 inches and standard deviation 1.26 inches. All right. So they both have the same mean, but notice how they're standard deviations. Okay. The first hybrid, hybrid A, has a larger standard deviation. Okay. So what does that mean? Well, that means that the blossoms for hybrid A are less consistent than those of hybrid B. So if you want a rose bush, okay, if you want a rose bush who consistently produces roses that are closer to 6 inches across, use hybrid what? Hybrid B. You see that? But you know, if you want a rose bush that may have a 10-inch blossoms or occasionally has a 2-inch blossom, use the first hybrid. See, the hybrid B, that data is closer to the mean than those of hybrid A. Okay, so that's why I worked the two examples like that, so you can kind of understand what's going on, what we're finding here. All right, so now we have population parameters. We got the population mean is mu equals the sum of x over n. The population variance is sigma squared equals the sum of x minus mu. Mu is the mean. X minus mu, all that squared divided by capital N. And population variance is equal to sigma equals the square root of that, where capital N is the number of data values in the population and X represents the individual data values of the population. And then we have the computation formula for standard deviation. You can see it's similar to the sample standard deviation, except notice down here we got n minus 1. Okay. All right. Now, let's just talk for just a second. I'm not going to get into a lot of detail on this, but I do want to bring it up. If you notice the difference in the formulas, we had S is equal to the square root of the sum of x squared minus the sum of x squared over n divided by n minus 1. This is the formula for the sample standard deviation. This is the formula for the population standard deviation. All right, so let's talk about that. I'm not going to get into a lot of detail. So you notice the formulas for the sample standard deviation and for the population deviation, that we use the n minus 1 here for the sample, and we use just capital N for sigma for the population. All right, so the reason, all right, so the capital N, this capital N here represents the population size, and little n represents the sample size. And since a random sample usually will not contain extreme data values, large or small, and do you know what I mean when I say extreme data values? That means data values that may be way off, okay, from the normal, from some of the numbers like outliers or something like that. We divide by n minus 1 in the in this formula here for the sample, okay. And that's really all I'm going to say about that. If you're really into this statistics and stuff and you enjoy it and you want to take more stat courses, there you can get into some theoretical statistics classes that show how all this works. But as far as for the scope of this class, or what class the students that are actually watching this, it's kind of beyond this class of getting into more detail on that. But there you go. Just a quick little explanation. All right, so the next thing I want to talk about is, yes, there may be a disadvantage of standard deviation as a comparative measure of variation, is because it depends on units of measurement. Like if you have two different samples, and one sample, its measurements are saying, I don't know, in feet or something, and you have something else and its measurements are in miles or whatever, or you may have pounds and stuff like that. Okay, it's difficult, it's hard to use standard deviation to compare the measurements from different populations. And that's why we have this coefficient of variation. it expresses the standard deviation as a percentage of the sample or population mean. Okay, so we're looking at a percentage rather than units of measurement. So the coefficient of variation, if x bar and s represent the sample mean and sample standard deviation respectively, then the sample coefficient of variation, which we'll denote that as CV, is divided by the standard deviation divided by the mean, the sample standard deviation divided by the sample mean times 100. That's going to give us a percentage. And the same thing for population. If mu and sigma represent the population mean and population standard deviation respectively, then the population coefficient of variation, CV, is sigma over mu times 100. All right. So let's look at this. It says, and once again, we're going to have we're going to do two examples like this. We're going to find the mean and standard deviation and coefficient of variation. For this problem, I'll show all the work on finding the mean and standard deviation, but on the next problem, I'm not going to show all the work because it's going to be work similar to this. All right. So the trading post on Grand Mesa is a small family-run store in a remote part of Colorado. The Grand Mesa region contains many good fishing lakes, so the trading post sells spinners. Now, for those of you that don't know what spinners are, they're fishing lures. All right. The store has a very limited selection of spinners. In fact, the trading post has only 8 different types of spinners for sale. The prices in dollars are, and there's the price of them. Since the trading post has only 8 different kinds of spinners for sale, we consider the 8 data values to be the population. Find the mean and standard deviation and coefficient of variation. All right, so let's find the easier one first. Mu, the standard deviation. That's where we add all of these up. So if we add all those up, we get 17.15. Divide that by 8. 17.15 divided by 8 is 2.14. We'll round it to 2 decimal places. All right, so there's the mean. Now let's find the standard deviation. So once again, we got x squared. And I'm just doing this example because the first 2 examples I did using finding standard deviation. And I think I'm going to move this down here. We've got x squared. And the first 2 examples, we didn't have decimals. Here we have decimals, so let's just do it with decimals. 2.1, 1.9. And I know here I put 2.1. That's the same thing as 2.10. 2.62. And then we have 1.85, 2.25, 2.15, and 2.25. So I just took each one of these values here and wrote them down. And then what do we have to do? Well, now we've got to square each one. So that's going to be 4.41, 3.8025. And yes, I've already got these squared. I'm just copying the numbers down. 3.4, 3.4225, 5.0625, wait a minute, I think I got off somewhere. Oh no, that's right. 4.6225 and 5.0625. And then remember, we want to sum each column. So the sum of the x values is 17.15. And then the sum of x squared is 37.14. 1425. All right. Now, remember, in this problem, we are talking about the population. Okay. So we're finding the standard deviation. So that's S is the square root of the sum of x squared minus the sum of x squared over capital N, and then that's divided by capital N. We're using that formula because we're dealing with the population. Why is it the population? Because this store only sells 8 different spinners. That's all of the spinners that they sell, so that's the population. And so we get S is equal to the square root, the sum of x squared, which is 37.1425, minus the sum of x, which is 17.15 squared, divided by N. Capital N is 1, 2, 3, 4, 5, 6, 7, 8. And then that's divided by 8. And, oh, I'm sorry, look at what I did. That's not S. That is sigma. We're dealing with population. And so I get sigma is equal to, that comes out to 0.22. So 22 cents. So there's sigma. And so the mean is $2.14. The standard deviation is 22 cents. Okay. Now they want us to find the coefficient of variation. So the coefficient of variation, in this case, that's sigma over mu, which is 0.22 divided by 2.14, and times 100. And so the coefficient of variation is 10.28%. All right. So there's your mean, standard deviation for that sample, for the prices there, and we found our coefficient of variation. Okay. All right. Now let's look at this next example. It says Cabela's in Sidney, Nebraska is a very large outfitter that carries a broad selection of fishing tackle. It markets its products nationwide through a catalog service. A random sample of 10 spinners from Cabela's extensive spring catalog gave the following price in dollars. So there it is. We got 10 of them. Find the sample mean and sample standard deviation and the coefficient of variation. So notice what it says here. It says a random sample of 10 spinners. Okay. So they have a lot more spinners, and we're randomly selecting 10 of them and writing the price down. So when we do this, when we find the mean, notice X bar. In the previous example, I used mu and I used sigma. Mu to represent the mean, sigma to represent the standard deviation, because this was what? This was the population, because that's all they had was 8 spinners. Now I'm taking a sample of all they have a lot more spinners, but I'm just only sampling 10 of them. So that mean is $1.87, and then the standard deviation, notice I'm using S for sample standard deviation, is 62 cents. And just, I want you to note that for this standard deviation, I'm using sum of x squared minus the sum of x squared over n, small n, divided by n minus 1. That's the formula we're using to calculate that standard deviation. Okay, and it's the same process. You'll make the chart out and everything and just pop everything into the formula. And in this problem, note that n is equal to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? All right, so the coefficient of variation is s over x bar times 100, which is 0.62 over 1.87 times 100, and that is equal to 33.16%. There's your coefficient of variation. All right. All right. So let's look at this again. Okay, we did two examples the same, because remember what I told you, it's kind of useless working all this stuff if you don't know what you're doing, if you don't know what you're finding, if you don't know how to interpret the results. Okay. All right. So notice for the trading post. So notice for the trading, I'm comparing trading post. The coefficient of variation was 10.28. Was 10.28%. And for Cabela's, the coefficient of variation was 33.16%. So notice the coefficient of variation for Cabela's was, it's, let's see, I guess, I don't know, it might be about 3 times. It's about 3 times more than the coefficient of variation for the trading post. So why is this? Well, it could be that, well, think about the trading post. What did it say in the problem? They're in a small town. They're not as big as Cabela's. Okay. And so typically when you have stores that are, just like in one little spot, versus somebody that sells nationwide, the prices tend to be higher, right? So that's going to make the mean larger. Okay. And also the trading post, they're small, so it's probably going to have a limited selection of spinners that has a with a smaller variation in price. Okay. So, that's how you can kind of interpret these things. So you can see finding this stuff, finding standard deviation, this coefficient of variation, it can tell us, we can compare two things. Okay. We can compare two data sets and interpret the results. All right, so let's look at this, and I believe this, this is the last thing, so just hang in there if you're still here watching. All right, so this is Chebyshev's theorem, and what I want to say about this is we're not getting real deep into Chebyshev's theorem for this video. I've got a lot more examples on this. If you will go search my channel for Chebyshev's theorem, I've got a video on just that goes into more detail and works more examples and different kinds of examples than what we do here. All right, so check that out. All right, so Chebyshev's theorem says for any set of data, either population or sample, and for any constant k greater than 1, the proportion of the data that must lie within k standard deviations on either side of the mean is at least 1 minus 1 over k squared. All right, and so here is here's some results of Chebyshev's theorem, and I'm going to explain more and get you to understand what it what this means. Okay, so it says at least 75% of the data fall in the interval from mu minus 2 sigma to mu plus 2 sigma. 88.9 is mu minus 3 sigma to mu plus 3 sigma. And at least 93.8 fall in the interval mu minus 4 sigma plus mu plus 4 sigma. So what this means is mu minus 2 standard deviations. So from the mean, we're going 2 standard deviations to the left and 2 standard deviations to the right. Okay, that's what it means. And let me show you this 75% here. So look at this. It says the proportion of the data that must lie within k standard deviations. So k represents how many standard deviations we are to the left and to the right of the mean. And in this case, we're 2 standard deviations on either side of the mean. Here, we're 3 standard deviations on either side of the mean. And here, we're 4 standard deviations on either side of the mean. So you can see in this first one here, k is equal to 2. Here, k is equal to 3. And here, k is equal to 4. So look, if we take 2 and plug it into the formula, 1 minus 1 over 2 squared, which is 1 minus 1/4, which equals 3/4, which this is what, 0.75. There's your 75% of the data fall in this interval here. And then the same thing here, if you plug the 3 in, that would be 1 minus 1 over 9, which is 8 over 9. And you can do 8 divided by 9, and you'll see you get this. Okay, see, that would be 1 minus 1 over 3 squared, which is 1 minus 1/9. Okay, and that's going to give you the 0.889. Okay, and then you could do the same thing with 4 standard deviations. You would have 1 minus 1 over 4 squared, which is 1 minus 1 over 16. All right. All right, so let's look at this. All right, so it says Dr. Gill has kept a record of X, which equals the total number of work hours volunteered by a student in a program each semester. For a random sample of students in the program, the mean number of hours was X bar equals 29.1 and standard deviation of 1.7 hours each semester. Find an interval for the number of hours volunteered into which at least 75% of the students in this program would fit. All right, so the data represents the number of hours that were worked. So we have a big list of data with hours worked. And we want to know in what interval will at least 75% of those values fit into. Okay, so we know at least 75%. So that we know that we're what? At least 75%, we know we're 2 standard deviations on either side of the mean. 2 standard deviations about the mean. So we know our interval is going to consist of the mean minus 2 standard deviations to the mean plus 2 standard deviations. And so for this problem, we're going to use, and we're dealing with the sample. So minus 2s, 2x bar plus 2s. Now I know you're thinking, well, up here you got mu and sigma. Why are you using x bar and s? Well, this right here was based on population mean, population standard deviation. It's going to be the same thing. We just have a sample. We have x bar and s instead because this is for a random. I spelt that wrong, didn't I? For a random sample of students. So we're just taking a random sample. We're not using everything, so we're not dealing with the population. And so now we just got 29.1 minus 2 times 1.7 to 29.1 plus 2 times 1.7. So there you go. So that's going to be 25.7 to 32.5. That's the interval. Okay, so at least 75% of the students would fit into the group that volunteered from 25.7 to 32.5 hours each semester. And that's the 2 standard deviations on either side of the mean. And let me just show you what that looks like. So we know the mean is 29.5, right? 29.5. And so what do we mean by 2 standard deviations on either side of the mean? So if we go from here to here, 1.7 units, that is 1 standard deviation. See, 1 standard deviation is 1.75. And then if we go another 1.7, did I say 1.75? If I did, I meant just 1.7. But look, this right here is 1 standard deviation. And this would be, that's from here to here. From here to here, say we go 1 standard deviation and then we go another standard deviation. So this would be 2 standard deviations. And same thing over here. If we went to this side 1.7 and then went another 1.7, this is 2 standard deviations to the left of the mean. This is 2 standard deviations to the right of the mean. And look, if you do 29.1 plus 1.7, that's going to give you 30.8. And then if you add 1.7 again, that's going to give you 32.5. And then the same way if you subtract 1.7 and subtract 1.7 again, that would get you to the 25.7. That's what they mean when they say 2 standard deviations on either side of the mean. But between these numbers, this is 25.7. So between these 2 numbers right here, at least 75% of the students would fit into that group right there. And that is all of this video, and I hope it helped. I hope you learned something. I hope you understand it now. But check out my other videos. Give me a like, share, subscribe, comment, and I'll see you in the next one. Later.